Hi. So the speaker today is Dr. Bellomo from the University of Palermo, Department of Physics. So he got the PhD in 2008 in Palermo, and he has collaboration with different people in Japan, in UK, and in Italy. And he's working in quantum information with main interest in open quantum systems and dynamics of quantum effects in these open quantum systems. And today we speak about revival of quantum correlation without system environment backup. Thank you.
Thanks, Roberta. Good afternoon to everybody. I want to thank Roberta again for inviting me here and for this opportunity to deliver this talk, in which I want to discuss some results obtained in collaboration with two my colleagues in Palermo, Rosario Franco and Giuseppe Compagno, and with Eric Anderson of Heriot-Watt University in Edinburgh. And this talk is made of two parts. The first one is of introductory nature. I want to start by discussing the physics of characterization of quantum correlation in quantum systems, how they have been quantified for which are the physical reasons. And I want to spend some words also about some known results about the dynamics of this correlation in open quantum systems. This will allow me to go to the second part, where I present some original results about the possibility to have a revival of quantum correlation in absence of system environment vacation. And so let me start by saying that, of course, the importance of correlations in physics, which are at the core of measurement theory, because in order to make measurements on a system, we need a measuring device, and it's the building up of correlation between the system and the study and our measuring device, which allows us to make measurements. And of course, correlations are relevant in the many body systems, where the change of correlation is strictly connected to important phenomena like quantum phase transitions, where we can have long-range correlations in the ground states of many body systems, or a superconductivity, so with correlation between the two elements of Cooper pairs and so on. I want also to cite here that, for example, if one thinks about the Casimir-Holder forces, this can be interpreted indeed in terms of the fact that from especially the electromagnetic quantized field is correlated in the vacuum state of the field. And going to other areas, we have also an important role of initial correlations in the theory of open quantum systems dynamics. And of course, the behavioral correlation with respect to space-time locality lead to the concept of entanglement, and I will speak briefly in the next slides about this. And of course, I will speak also about quantum information processing, which want to exploit the presence of correlations in order to perform certain tasks. So, I just decided to speak a little bit about Thom's and Einstein-Podolsky-Rosen pairs in the version by Bohm, where two spin one-out particles are considered, and essentially after some interaction, the system can be described by some kind of a single entity, which we call entangled states, where, for example, using the superposition principle, we can superpose state like these ones. So first, for the first particle, we have a spin. The spin has only two possible outcomes in the measurement only along a certain direction. So we can have, for example, particle A prepared in spin up and particle B in spin down, and we can subtract the opposite state. What we obtain? We obtain a single state which is independent in the form for relations. What is important here, and what is that in this case, no system has a well-defined state on its own. So this means that we can to describe with certainty the state of ρ, we have a statistical mixture describing the the state of one of the two particles. And as a consequence of this correlation between the two particles, if one performs measurements on a particle, no matter how much is the distance between the two particles, we have consequences on the structural probability outcomes in later measurements on particle B. Meaning what? For example, if we measure the spin of particle A and we find the spin up, automatically we are certain that particle B will have the spin down. So there is an influence due to the measurement which is connected to the fact that the two particles were strongly correlated between them. And this kind of study led to the concept of entanglement and separability dichotomy, where essentially we define a class of states that we call separable states, which are essentially convex combination of product states where P con E plays a role or a sort of classical probability distributions. If this can be done, this cannot be done, we call the state entanglement. And in this context, for sure, one of the major contribution to the understanding of the role of correlation in quantum mechanics is due to John Bell, which showed that for any classical local model which invokes the presence of some kind of locally hidden variables we don't access, if this local model can describe our system, as a consequence, if we perform measurements of some kind of property on A and on B by varying some kind of settings, for example, we perform spin measurements on A and B in different directions. When we collect all the outcomes, well, some kind of inequality must be satisfied. If this does not happen, well, this means that our classical local model cannot describe our systems. And indeed, quantum mechanics may violate this inequality. So this kind of violation has been observed in a huge amount of experiment and leads to the conclusion that non-locality is an intrinsic property of quantum mechanics, and non-locality is connected to the presence of correlation between the parts of our system. So, even if this kind of result tell us about are really profound and are connected with the basis of quantum mechanics, the explosion of studies about the role of correlation, about how we can manipulate them in quantum system, is not connected to this kind of observation, but about the application, how we can exploit the presence of correlation. So I am speaking about quantum information processing, where it has been recognized that we can exploit these correlations in order to perform certain tasks better than in a classical way. Here, the element of information 0 and 1 of the bit are coded in a two-level quantum system, and the possibility to prepare our two-level quantum system in a superposition of both the 0 and 1 is at the basis of several applications, like quantum computing with the speed increase, quantum cryptography, where one uses quantum communication in order to cryptograph the key or to break down the cryptographic systems, and quantum teleportation, where we use entangled states in order to teleportate states of a qubit from one location to another one. So, however, even if we are speaking in a good sense about entanglement, indeed, but several authors identify, even if entanglement has been often identified with quantum correlations, several authors pointed out that even using separable states, so where entanglement is not present, it is possible to exploit quantum systems in separable states in order to have improvements for certain quantum tasks. Improvement with respect to the best known classical strategy to solve that kind of problem. So in this context, we can cite, for example, quantum search without entanglement, the use of separable states for the Dipartimento problem, or for example, the use of separable states in the first experiment about the simulation of quantum computing with nuclear magnetic resonance, and some kind of deterministic quantum computer model with one qubit where separable states are considered the key ingredient for the speed up. So this observation led to the necessity of investigating quantum aspect of correlations other than entanglement. And the approach in order to do this, we start from the classical case. And we say, okay, we have two random variables, A and B, and we want to quantify the correlations present between these two variables. In order to do this, we introduce a joint probability distribution for the outcomes of the two variables, the marginal probability distribution, and a Shannon entropy to quantify the uncertainty in each variable. And the correlation between the two variables classically are quantified by the Shannon model information, which essentially is the sum of the two entropies, reduced entropies minus the entropy of the joint probability distribution. So the point here is that classically you can interpret this quantity in two different but equivalent ways. First way is we introduce some kind of quantifier for the distinguishability between two general probability distribution that here I call PA and PB. How much are distant, how much they differ. We use Shannon relative entropy to quantify this distance between the two variables. And we compute the distance given by Shannon relative entropy between our starting joint probability distribution, PAB, and the product of the marginals where we have erased all the correlation initially present. This distance coincides with Shannon mutual information. So this is the first way to look at Shannon mutual information, the distance between starting a distribution and the product of marginals. But there is another way to look at this quantity, which makes use of conditional probabilities, meaning that we can ask about which is the probability to observe Bj if we have observed Ai for the random variable A. So we introduce this kind of conditional probability, the conditional entropy, and the Shannon mutual information is equal to the information that we convey about B thanks to the measurements of the random variable A. Meaning, in another way, that quantum Shannon mutual information coincides with how much we have reduced the uncertainty of the variable B thanks to this kind of measurements, to this knowledge on A.
These two ways of measuring always produce the same result?
Are?
Always produce the same result?
In the classical case, they are equivalent thanks to the Bayes rule.
So there is no possibility to give a different result one way or
No.
another?
No, they are equivalent for construction. Just using this definition of conditional probability, they are equivalent.
And in practice, when you evaluate on a given set of data,
Sorry?
if you evaluate that on a given set of data, is
Yes.
one way more efficient than the other to be evaluated, or this?
No, they are
I mean, you
to
have
compute them.
you have to compute on a finite number of data points and whatever.
Yes.
It will give.
To my knowledge, is the difficulty in computing is the same.
The same.
I don't know. Maybe it could be better if one has access to this kind of numbers instead of other ones, but there's no difference. But this is not the case in the quantum case, in the quantum version. And in fact, we will exploit this difference in order to quantify correlation in quantum states. So, first of all, we go to quantum case, and now the protagonists are, we consider butterfly system. So now we have the total state rho, we have the marginal states obtained by tracing out the degrees of freedom of part B, for example. And we have, instead of Shannon entropy, we have the analogous for normal entropy. And first generalization is obvious. We take the definition of Shannon-Mutter information, and we use for normal entropy, we use the marginal states and the total states, and we obtain this expression, which has been called quantum Mutter information. This quantity, many others have decided to use this quantity as a quantifier, as a good quantifier for total correlation. And for example, some arguments are linked to operational interpretation of this quantity in terms of you have a state, you want to know how many correlations are present in that state. Okay, you make the following reasoning. You say how much noise I have to use in order to lead our initial state to the product and marginal, how much work I need to erase these correlations. And they have shown that in particular the minimum rate of randomness is equal to this quantity. We can also cite communication consideration, where in certain quantum tasks, for example, it has been shown that the maximum amount of information that can be sent securely from two guys is equal to the quantum Newton information. So let's say at this point that this has been identified as a good quantifier for total correlations, but now what we want, we remember, we wanted some kind of quantifiers for quantum part correlations, different from entanglement. So the approach we use here is the one based on these two papers, which essentially want to distinguish the truly quantum part from the classical part of correlations, and so starting point, the other version of the classical model information. If classically we were just considering a possible knowledge of the outcomes of A, here in the quantum case, of course, how much information we get on B depends on which kind of measurement we perform on A. So it depends on the measurement we do. So we consider a complete measurement. In particular here, in this moment, we limit it to the case of one-dimensional projectors, which we indicate in this way, and we write down the state of B after the measurement on A, by considering all the possible outcomes on the part A. So we have several outcomes on A. For each one, we have a different final state on B. We can construct what? A conditional density operator, which keeps into account all the possible outcomes on A. We introduce a quantum conditional entropy about the uncertainty of the state, and in this way we can construct the analogous quantity, the quantity analogous to this one, making the difference between the entropy of the reduced state and the entropy of this conditional density operator after the measurement on A. But in this way, we have a quantity which depends on the measurement we have performed. So, keeping in mind that this difference is how much we have reduced the uncertainty on B thanks to the measurement, we take the maximum of this quantity. People took the maximum of this quantity in this way, and they've shown that this quantity satisfies reasonable properties that one imposed for a good measure of classical correlation. So we start to say this quantity must be invariant for unitary operation, must not increase for local operation, and so on. And they have shown that this quantity is a good quantifier from this point of view. So at this point we have a quantifier for total correlation, we have a quantifier for classical correlation, And independently, Oliver and Zurek decided to introduce a quantum discordance as the difference between these two quantities. And so at the end, we have quantum discord, quantifying quantum correlations, classical correlations, and total correlations, linked by these kind of relations. And so we introduce quantum discordance as the difference, and we observe several things. First of all, this kind of measurements is not symmetric, because we decided to perform measurement on A, but we could decide if we perform measurement on B, in general we have a different result. If, of course, the state is symmetric, this is not, but in general it is. So this is not symmetric, and in general, zero discord states have this form, where phi k, at least for two-qubit systems, are pure states. In many cases, they are orthogonal states for sure. And so, if one maybe to have another point of view, we have that, of course, if we remember the form of separable states, here we have a constraint more. The states on A are pure and often orthogonal between them, while before they were just possible states. These already tell us that in general, quantum discord may be present for separable states. In a separable state, the discord may be different, and if one believes in quantum discord as a good quantifier for quantum correlation, it means that even if you have a separable state or no entanglement, in this way we have quantum correlations. And in particular, in order to justify the fact that we want to call quantum correlations this kind of correlations, so we can cite the fact that the presence of discord has been identified as a resource for one qubit deterministic quantum computation and in other kind of protocols for quantum information. And in particular, I want to just to give also some other information about a recent operational interpretation of Diderot in terms of a well-known task in quantum information called the quantum state merging, where in a tripartite configuration, one part wants to send its state to another one. So, this is important because each quantity must be in some way related to some kind of protocols you want to implement. And another interesting point I want to stress is that, of course, as I already said, classical correlations and discord require in general a minimization over all possible PRVMs, all possible kind of measurement we want to do on system A. And but in the case of two-qubit systems, this minimum is reached using just projection on the pure states, and it has been conjectured that maybe also just orthogonal states is sufficient to obtain the minimum. So this slide is just to stress the difference between entanglement and discord by making an example where we compute both quantities. So in particular here we take maximally entangled states, which is a superposition to 0, 0, 1, 1. We add some noise. So adding noise, we go from a maximal entangled configuration from a maximal entangled configuration towards below a certain threshold, we get a separable state. But if we compute the discord with respect to this z parameter, we can see that discord is present for any value of z different from 0. So this is just an example where a separable state can have a discord different from 0. And okay, of course, this is not the end of the story. There are a lot of approaches in when one wants to discuss quantum correlation, I want to cite another one, which is based on the concept of distance between states. And the main idea is the following. We divide all the states, all the physical states in various groups. For example, we have the family of product states. This approach is interesting because it's easily applicable from a formal point of view to the n-partite systems. So here I give a formula for n-partite systems, not only bipartite. So product states, no correlations. They are just factorized states. Each part is in a well-defined state. Classical states as a mixture of locally distinguishable states, meaning that for each part various k are orthonormal between them. So this is a possible definition of classical states that, for example, differ from other choices of ours. And separable states, which we encountered before in the bipartite case. And so in this way, how we introduce quantifiers? Well, we say we have rho, we want to know how much is the entanglement in rho. Okay, we look at the class of separable states, we introduce a distance, and we look for the state which is the closest one between inside the class of separable states. This distance is a quantifier for entanglement. And this has been used in the literature, and the quantifier of distance typically used is relative entropy. Relative entropy, which is defined in this way, is connected to the fundamental entropy. And following this idea, we can introduce all the quantifiers we want. For example, this chord is the minimal distance between rho and the class of classical states, and TD rho is this minimal distance between rho and the class of product states. This minimal distance coincides with the case when P greater rho is the product of the marginals. So this means that this approach gives as a total correlation quantifier quantum model information. So in this sense, there are in several aspects this approach gives analogous quantities for the quantifiers. And score? Okay, well, we, in a sense, once discussed the physics of the characterization of various kinds of correlations in quantum systems, we want to exploit them in dynamical contexts. So our interest in investigating the dynamical properties of these quantifiers, why we are interested in this. Let's say that in general, if, for example, we think about the practical implementation of quantum systems in quantum information, of course, all the protocols many protocols make use of states, correlated states. So, but due to the interaction with the degrees of freedom of the environment, this correlation gets lost in general. So if we want to seriously think about the implementation of quantum computing, we need to know the rule of how this correlation gets lost due to the interaction with the environment. So in general, this is an important problem. And an incredible amount of work has been dedicated to the analysis of the dynamics of correlation quantifiers in open systems. In particular, here I want to recall some results about the dynamics of entanglement. First one is a sudden death, and so we have two qubits which are subject to a Markovian noise, and it has been shown that even if for each qubit the internal coherence may decay, for example, at infinity with an exponential decay, the entanglement between the two qubits can vanish in a finite amount of time. So this process has been named entangled sudden death, with the name, which recall us that we are not happy for this phenomenon because the time of usefulness of entanglement may be reduced in front of our expectation, looking only at the internal players. But it has been also shown that when one considers other kind of environments where memory effects are important, we can also have that correlation may revive in our two-qubit systems, or even may be trapped by considering certain spectral density from the environment. But we will come back to this a little bit more in detail later. Here I want to cite the fact that analogous studies have been conducted for the case of a quantum discord, classical correlations, their behavior in Markovian, non-Markovian quantum environments, local environments, common environments, and presence of interaction, and so on. And maybe a result it is worthwhile to cite is that in general, quantum discord results to be more resistant to the action of the environment. For example, in the case of Markovian dynamics, no sudden death may occur. So even if we, by looking at entanglement, we get the impression that we have not any more quantum correlations in our systems, if we look at the quantum discord and we believe it as a good quantifier, we have we can have get a quantum correlation. And another interesting phenomenon is the possibility to have some kind of dynamics, so some kind of environments, in which, for example, classical and quantum discord can be alternatively frozen. So, for example, we have total correlation, which decay in a regular way. We decide to split total correlation to parts. We look at the discord, and in the first part it's just the classical correlation which are going down, while discord are not. And well, this can be exploited in, for example, for quantum information, because these tell us that we can have a time region where quantum correlation are frozen, but it can be also used, for example, to imagine to construct an environment where you have an initial state which is correlated. You put this system inside the quantum environment which make decay only the quantum part of correlations. At the end you have a system which has only the amount of classical correlation which were initially present. So this can be another operational interpretation of classical correlation in quantum state. And however, between all these phenomena in open quantum system, our main interest is on the occurrence of revival of correlations. And I want to stress an important point. Of course, if you consider a system where a direct interaction is present between the two qubits, interaction create correlations. So if for some reasons the interaction with the environment make decrease in entanglement, it disappears. If there is a direct interaction between qubits, in general we can expect that a correlation can revive. Another possibility is not to have a direct interaction, but a mediated one. Mediated by what? By a common environment, for example. We put the two qubits are in the same cavity, are close enough to have the correlations of the environment responsible for some kind of indirect effective interaction. So we look at another configuration where there is not interaction. The environment are a local environment, not common environment. So the environments don't speak between them. And in this case, in the Markovian limit, we have certain that. But in the non-Markovian limit, it has been shown that the presence, the memory of the initial state, the presence of memory effects on the dynamics can be responsible to coming back of correlation from to the two qubits. So in general we speak of revivals and trapping. And the point here, the main point, the starting point for the results I want to present is why these, the interpretation of these revivals. And in particular, these revivals have been interpreted in terms of cyclic exchange of correlations due to backcaching in our system. So let's fix the ideas by thinking about two qubits in two different cavities, and the cavity may lose photons outside. So we have qubits, we have the cavities, and we have the reservoirs. If the two qubits are initially entangled, if one looks at the other part of the system, discovers that correlations build up between cavities, correlation build up between reservoirs, and if there is enough time to interact again with the two qubit systems, if the dynamics is non-Markovian, and it can be, we can have exchange of correlated excitations between the various parts of the systems. So the interpretation is exchange of correlations due to the backcaching. However,
sorry, I lost.
Yes.
Two parts of the system, two reservoirs, each one has some memory effect in its own reservoir. I don't understand.
The memory effect is in the dynamic, each one qubit, another qubit.
Mm-hmm.
Each one is inside the cavity,
Yeah.
but the cavity has some losses. So they lose the photons through the reservoir. And the internal dynamics of each qubit with its cavity in general is going to present memory effects. So in some means, of course, if the coupling is strong enough. So in this limit, you can have this kind of behavior of the entanglement between all the various parts. So for example, if you look at qubit, the correlation, here entanglement is quantified by
you put it as an initial condition. You need to put the entanglement as an initial
okay, I'm
condition.
sorry, of course this is a main point. Nothing happens if initially the two qubits are not entangled. It was obvious, but otherwise we have the two independent parts, and each one of those, and nothing may happen. So the point is that initially, of course, the two qubits are prepared in an entangled state. Okay. No, this is, of course...
There's no coupling between qubits, nor cavity, nor reservoir.
Sorry?
There's no coupling between qubits, nor cavity, nor reservoir.
No. Just the two qubits are initially prepared in an entangled state. So it's the memory of this initial configuration which is responsible.
But if you put some coupling, that might enhance that, and the fact that they interchange some
if you
information.
put some interaction,
Yeah.
of course you can, for example, have stronger revival correlations. Interaction means possibility to create the correlations. But here I want to just focus on these systems. Why? Because here we don't have this kind of source of correlations. Here we have this kind of interpretation, exchange of correlated excitation. However, it has been shown that, for example, for classical environment, we can have entanglement revivals. And so we now define our interest, which is to consider the system unaffected environment. It means environments which have some properties which cannot be modified by the interaction with the system. So no backcaching. The environment just behaves as some sort of external pump which cannot be modified by the interaction with the system. So no possibility to have exchange of correlated excitation between the qubits and the external reservoirs.
And when you say no backaction, means that it's something beyond the fact that the environment is an infinite system and its state is not modified by the system, which is the typical assumption that what is
This could be a possibility. But in that way, you can think about that our result is for example, is connected to some kind of approximations. But here we will take something that okay, in a sense that is always an assumption that you can neglect some kind of things that goes to the environment. But here we will take a classical external function, where they have some parameter which cannot be modified by some kind of back action of the system and the environment. So in this sense, the environment is not modified by its interaction with the system. I will describe the model in the next slide. So the questions are how one can explain revivals of entanglement in this kind of systems, and the other kind of correlations we spoke about. This is called the classical correlation. Behavior can be subject to revivals, and we want to answer to these questions just looking at accessible quantities. That it means the dynamics of the two qubits. So we do this in this model. We have two qubits. These red lines is just to say that the two qubits are initially in a correlated state. So we have a correlation between the two qubits. But the two qubits are far enough that the interaction is zero, no interaction between the qubits. Each qubit is subject to random external fields. What it means? With a certain probability, that here we fix 1/2, the qubit is subject to an electric field with a phase phi1 equal to 0. With another probability, which is 1/2 of course, it is subject to an electric field with another phase, pi in particular here. So if we want to follow the dynamics of the qubit, we just need to sum the two different stories. We have two possibilities, or phase 0 or phase pi. We follow the two stories, and after we make the combination, we have the statistical description of the state at time t. So this is the map which lead our system from 0 to its configuration at time t. Thanks to the fact that this action is local and there is not interaction between the qubits, from a technical point of view, the global map of the two-qubit system is very easy to write, because you take your initial configuration that is correlated, and you have to follow just the 4 possible stories: 0, 0, 0, pi, pi, 0, pi, pi. No? So we have 4 possible way of evolving for the two-qubit state, and we have to consider all the possible stories. And we have our system at time t. So
I mean, the environment is very static?
The environment is the main point. I want to stress it already here. So, the environment is not
It's not a
modified.
dichotomic noise, it's a constant noise, either pi or 0.
Either
But
pi
always
or
zero
0.
or always
There is
pi?
not fluctuations like chance. This is the main point. You have different story not communicating between them, or 0 or pi. If it's 0, you follow a 3. If it's pi, another 1. But of course you don't know, so you need to follow both the stories. And so, just a little bit of notation. We call the 1 excitation and 2 excitation Bell states in this way. We consider as initial configuration what is called a Bell diagonal state, which means a state which is diagonal in these correlated bases. So the eigenstates of our states are always the maximally entangled states. We have an initial configuration of this kind. We make our map evolve with the systems, and we remain inside this class of states. At time t, we have always the Bell the maximally entangled best states as an eigenvector of our density matrix. But with the coefficients which evolve, the coefficients change. How they change? They change with, in a way such that after a certain time or after a certain amount of time, the systems come back to the initial configuration. It means that the model is constructed in such a way that the dynamics is decided. What is the consequence of this? The consequence is that even if we have local fields which have characteristics that are fixed, they cannot be modified by the interaction with the qubits, if we look at correlation, we discover the following behavior. Total correlations behave in a regular way. It's the green line. We split total correlation into parts by using discord and cluster correlation. Discord may be frozen, decay, and revive. Cluster correlation may decay, be frozen, and revive. So in this simple model, we can have all the phenomenology we have described before in encountering various systems here present. And in particular, we have the possibility to have building up of correlations even in absence of a back action induced the correlation exchange. But of course we want to look also at entanglement, and we compare it with discord, and we see that we have a similar behavior. So revive, so entanglement may increase after being decayed, and the difference is that we don't have the frozen regions for the entanglement. And so, in a sense, this okay. The result is that in this simple model, yes, it is possible to have revive for all kinds of correlations with the system and affected environments. So I kept this slide, which has been done by Saro Franco, who likes this kind of animation. But here is just to say what that okay, the initial two-qubit correlations cannot be temporarily stored as a correlation between the qubits and the environment, or between the environment and after that coming back. This is not possible here. But however, we have revivals. So, last slides are about the interpretation of this phenomenon, and we will focus on the fact that by looking at the form of the map, one can see that non-Markovian effects are present in our systems in the following sense. Let's focus on the state of the system, or the state of the two qubits at time tau1, t1. This is the time when entanglement and discord are zero. Let's imagine to start again from the beginning, but from this configuration. So we put the qubits in this configuration and we make our fields act. Well, in this case, nothing happens. No correlation can be built up, because of course the two fields are, the environments are local, so we cannot have a creation of entanglement with this kind of external fields. But so what it means that if we start from this state, nothing happens. But if we reach this state coming from a correlated state, in this case correlation can increase again. This is nothing. This means that we have a memory effect in the dynamics, and is the non-Markovian character of the map that is responsible of this possibility to increase, and is not connected to the exchange of correlations with the standard process. It's an intrinsic property of the map governing the dynamics of the single qubits. And from a formal point of view, this can be seen by, for example, showing that the map does not satisfy the Markovian composition law, so that it is not possible to separate the dynamics and several pieces using always the same form of the map. So we have this kind of effect. You have, you recall where you come from. in the non-Markovian limit. And how we can make this association more strong, more compelling, let's say. And okay, we need a quantifier of the degree of non-Markovianity. We have a system where non-Markovian effects are not really important and the system strongly non-Markovian. So we look at the theory of non-Markovian quantifiers, non-Markovianity degree quantifiers, and we take the one introduced in this paper, where essentially we have a qubit subject to some noise, and we want to quantify the eventual degree of non-Markovianity in this analysis. So what they do, they consider an ancilla qubit, they prepare system and ancilla in tangle states, and they look at the entanglement between these two systems under these dynamics. If there is some kind of increase of entanglement in time, so this quantifier registers this coming back of entanglement to the system ancilla configuration. So we take this quantifier, we compute in our systems, and we compare it. It's the green line, and here it's a scaled quantity of the quantifier, and we see that the non-Markovian quantifier increase in the same time regions where we have building up of correlations. So in a sense, this makes more quantitative the connection of the occurrence of the revivals and the degree of non-Markovianity of the map of the single qubits. So I conclude by recalling that in the final part of this talk, I have considered a model of two qubits prepared in a correlated state. We have a local environment, which are classical random parts essentially. The effect of this environment is to have collapses and revivals of entanglement, decrease and increase of discord and classical correlations, even if the environment is unaffected by the system qubits. And we have interpreted this not in terms of back-action-induced correlation, which is absent, but in terms of internal non-Markovianity of the single qubits. And I conclude with this. Thank you very much.
Any questions, comments?
Do I understand correctly? If can I say that the non-Markovianity in the dynamics is because the external field is frozen in time, and you substitute this by a fluctuating up and down 0 and pi noise? Probably this after several frozen times the revivals will decay until they don't occur.
This is our expectation. Indeed, before going to this simplified version, we look at some kind of phase noise laser. So a model where the field has a phase which can fluctuate with some kind of statistics. And in that case, of course, you don't expect cyclic evolution. Depending on how much the phase, which kind of noise makes the phase fluctuate, you have in general the same kind of plots but decaying. So in general, we expect
this is well, I don't know in quantum classical statistical mechanics is normal. You have quench noise. The effective description of the variables subjected to this is non-Markovian in general. Yeah.
Yeah, in this case, if we introduce this, we in some sense this is the limit where that effect is not considered. Maybe it is important later. But in order to observe that we can have this kind of phenomena, we didn't need to include that kind of effect. But you can include, and we expect similar behavior.
You go back one slide. Yeah, in pi4, the non-Markovianity has to be different from 0, isn't it? But even if it's very, very small. Otherwise, the state with memory and an initial state which begins there, you should have the same evolution. So the non-Markovian.
You expected that this quantifier must be different from 0 already here?
Already there.
This is not, but because their quantifier may increase only where entanglement change of direction. If it is decreasing, the quantifier begins to increase only when the entanglement change of direction. If it was decreasing, it must increase in order to have the quantifier increasing. So in the first part, entanglement is just decreasing, so the quantifier is not. But I don't know.
So it's about quantifier because it should be different from 0 there and also about the minimum.
No, in the other, for example, in the second minimum, is not 0 because the quantifier collects all the previous story. So it remembers that in these regions entanglement were increasing, so the quantifier increases. And after that, it stops here because entanglement is decreasing. So this is
So just quantifying the accumulated.
He is accumulating it in some sense. But I mean, the quantifier, of course, huh? But you must write a plan here. No, this is a possible quantifier, of course, but I mean, the fact that the degree, the map is not Markovian can be seen in different ways, of course.
Any other question, comment? No? If not, let's send Bruno again.
You want to say that in this moment, non-Markovianity is 0?
It should be different.